With our regression lines in mind, we can now talk about the main application we're going to see here, as well as really the main application that there is for regression, that being making predictions. Seeing as the data that we're working with isn't always going to include every single possibility for the two data sets that we're talking about, it's nice, it's useful, it's meaningful to be able to make predictions about what happens at those gaps, and for that matter at the points that are beyond what we might expect. However, we do have to be careful of two things that we've talked about a little bit already. The first one being that we should be mindful of what goes on with the residuals. When we're setting up these types of systems, we always have to leave some room for error in mind with those residuals because we're not going to get perfect linear relationships very often. So we just have to be careful that when we make our predictions, we know that there are some gaps in there to work with. That if we have a negative residual, that means our prediction's a little bit low, and if we have a positive residual, that means it was a little bit too high. So we should just bear that in mind when we're talking about what things we're expecting outside of the data set in terms of what things we do have to begin with. And on the other hand, when we're dealing with predictions, we should try to avoid making ones that are unreasonable. That is, we should try to stay reasonably close to our data set and also understand that some of the things we're going to see are a little bit theoretical. They don't exactly work in the real world. That if we have a data set working in, say, $50 or tens of dollars around that, we probably don't want to make a linear prediction on what happens around $1,000. The information we have really has no bearing at that level, so we shouldn't try and make a prediction based around that. Similarly, depending on what we're looking at, we may end up inching towards negative values, and in some contexts, like money, having negative value is meaningful, but in other ones, like height that we talked about earlier, or a number of dates, a negative value doesn't really have a meaningful sense to it. It doesn't really work in the real world. So when we're trying to make these predictions, we do have to bear in mind that there are some limitations we can work with and that we need to work within. All that said, it's a lot of words for now. It makes more sense if we look at this in the context of an actual example, which is what we're going to finish this section with by taking yet another return to that GDP and CO2 emissions data. So for the GDP data, given that I made a typo earlier and y hat should equal 199.535x plus 56.036, we want to predict the CO2 emissions for the following GDPs: $1.2 trillion, $2 trillion, and $14 trillion, which as of 2018 was the GDP of China. Where to do this, what we want to recall first is that the data sets we're working with do have significant linear correlation, and while we can do this with any regression line that we have, generally we want to be sure that we're doing something that isn't completely ridiculous. We want to be sure that we're not going way so far out of bounds that whatever we get can't actually be seen as having meaning because there was no regression. I don't always expect you to run an entire test first just to be sure, but generally speaking, if you're going to use this type of process, it is the baseline to get started here, because it's really a complete waste of time to try and make a prediction based on a relationship that doesn't actually exist. Anyway, seeing as we do have that, if we want to get our values, all we need to do is just plug them in. So, for our first case, it's really as simple as it sounds. To get the predicted value y hat at $1.2 trillion, you take that 199.535, multiply in the 1.2 for that x value we're trying to get the prediction around, and add that intercept value of 56.036, which is kind of like our baseline, our bottom that we're working with here, to get a prediction of 295.48 million metric tons, as it were. So exactly the way that we did when we wanted to check that residual in the last example, we can do here to make a different prediction where we're trying to get something that we don't already know. Just bearing in mind that it's probably not going to be perfect, but it's definitely better than having nothing. Next, for that second case, we're going to do the same thing. We're going to get a predicted value y hat by plugging into that 199.535x plus 56.036, a value of x equals 2.0. You need to put in the 0.0, but hey, it's good to be sure. And as a result, when we make this computation, we're going to end up with a predicted value of 455.11 million metric tons of CO2. That's the expectation there based on our model. And then finally, for the third case, well, we do the same thing again. Except now we should be a little bit more careful, we should be a little more thoughtful about this, remembering where our data mostly fell before, that we don't have a whole lot around the number 14. So what we get here might not be quite so meaningful. Anyway, we take that 199.535, plug in our value of 14, adding that 56.036, and we will get a predicted value of 2,849.53 million metric tons, where if we wanted to check this for ourselves, because this is an actual data point that you can look up online, you would see that China emitted about 1,006 million metric tons. And again, like I mentioned at the beginning of the video, it's important to understand that the further we get away from our data set, the less reasonable we should expect our predictions to be. So note here, not just because we know from reality how much CO2 China emitted, this is not, let's just say isn't, because I already screwed up my kerning, a good estimate. Where it's not a good estimate not just because it doesn't fit reality, but it's also not a very good estimate because we weren't looking at things above 10 from our data set to begin with. We were looking at things a fair amount smaller. And as a result, we got a bit of a jump. We got a bit of an unreasonable value here looking at that data point. So be careful when you're making these estimates to not draw too far outside the lines. Always pick values, always work with values that are actually meaningful to the data that they're meant to fit into. Otherwise, as we saw, well, you might get some funky errors. And these sort of funky errors, in terms of things like residuals, can also be discussed in terms of variation, which is what we're going to look at in our last section of the semester, 9.3.